In this short video, we're going to learn what some of the MPI functions do using an example program here. The example program really doesn't do anything constructive, just exercises a few routines so you can see what they do. So this is an MPI Fortran program. Let's run it with 4 processors. I'm going to show you the output when we run with 4 processors. And each processor runs exactly the same code, but at the beginning they call this routine here COM rank. You always want to call these 3 at the beginning, and it comes back with what task number you are. Well, you can call this and it'll tell you how many processors there are, and there's going to be 4. And then they call and ask, well, which one of those 4 am I? And it'll come back with either a 0, 1, 2, or 3. The 4 processors will get 4 different numbers, 0, 1, 2, and 3. So iTask tells you which processor your number you are, and NPES tells you how many processors there are total. And first we're just going to set, on each processor, we're going to set an array called sendBuff to 10 times iTask plus I, where I goes 1 through n, and we're setting n to 7. So processor number 0, iTask is 0, and sendBuff of I is just I, so 1, 2, 3, 4, 5, 6, 7. For processor number 1, iTask is 1, and so that'll be 11, 12, 13, so forth. So initially, the 4 processors have this data stored in their sendBuff. Okay, the first routine we're going to look at is called MPI gather, and what that does is takes the everybody sends their sendBuff in with n is the length of that array, which will be 7 here. And well, this tells you that it's an integer array, but they could be double precision or real. And one of the processors, iRoot, which we're setting to 0, we're going to let iRoot be the processor number 0, but it could have been any of the 4. I could have set it to any of the 4, but we're going to set it equals 0. So this means this MPI gather, everybody puts in their sendBuffer, and processor 0, and only processor 0, receives them all in an array called receiveBuff, which is basically going to have all 4 sendBuffs in order. First 7 elements will be the sendBuff of processor 0, the next 7 will be sendBuff in processor 1, and so forth. And since we've dimensioned receiveBuff to be n comma 10, where that 10 could be anything 4 or above, it's going to put the there'll be contiguous 4 groups of 7 in memory, but dimension like this, the first column is going to be the sendBuff from processor 0. The next column of receiveBuff is going to be the sendBuff of processor 2, and so forth. And so at this point, all this does is processor 0 or processor iRoot, whichever one you choose here, is going to basically gather everybody's sendBuffs into one big 4 times as long receiveBuff. And now I write it out just so you can see what's in receiveBuff, but I only write it out for processor 0 because it's the only one that has anything in receiveBuff. So I print it out, and has what we would expect. So here's what's print out by processor 0, the root processor. 0, see, it identifies itself as processor 0. And the first 7 elements are the sendBuff from the first processor. The next 7 elements are the sendBuff from the second processor, and so forth. So that's what we'd expect. Now these MPI barrier routines, we'll talk about those in a moment, but basically all they do is just hold everybody up and says, well, wait till everybody gets this far and then we'll go on. So they'll all stop there until they're all there, and then they go on. And now we have a scatter, which is the opposite of a gather, and this time the root, which is still 0, is going to scatter its receiveBuff, which remember contains the 4 processors sendBuff, and it's going to send those back to the 4 processors in an array called back buff. So receive buff is going to be 4 N elements in it. Back buff is going to have only 1 N elements in it, and receive buff comes from root and back buff goes to everybody. And of course, this is designed so that basically just scatters it back. So back buff should be exactly the same on each processor as send buff, because all we did was gather the 4 send buffs into one receive buff on the root processor, and then the root processor scatters them back. But instead of calling it send buff, it scatters them back to another array, back buff, just so you can see that it's going to be the same as send buff. So it's, and now we everybody writes out their back buff. And you can see that back buff is the same as send buff. Processor 0, its back buff is 1, 2, 3, 4, 5, 6, 7. Processor 1, it's 11, 12, 13, so forth. So basically the back buff is exactly the same as send buff on every processor, because it sent it into the root processor and gathered it all into one big array, and then it's scattered back. Okay, we're up to here, and there's another barrier that holds everybody up until all processors are to get there. And then now MPI reduce, what that does is it takes everybody inputs their send buff, which is still it hasn't changed, and root processor, which is still 0. This iRoot was set to 0 again. It could have been anything, but so the root's 0 processor is going to be special here. Then everybody puts in their send buff, and since this says MPI sum, then everybody, no, not everybody, just the root, just this processor gets its array back buff is going to be the sum of the send buffs. There's n elements, n being 7, so these are both vectors of length n. And the first element of back buff is going to be the sum of everybody's first element of send buff, and so forth. And MPI integer says that all these are integer arrays. MPI sum says add them. If you say MPI min, then back buff of 1 will be the minimum of everybody's send buff of 1, and back buff of 2 will be the minimum of everybody's send buff of 2, and so forth, or maximum, and I believe there's some other possibilities there. And so at this point, processor 0, its back buff should have the sum of everybody's send buff, and then we write it out, but only on the 0 processor, because it's the only one that has the sum there. And you can see that processor 0 writes out its back buff is the sum of the send buffs. Here, this is 1 plus 11 plus 21 plus 31 is 64. Add those up, you get 68, and so forth. So basically, MPI reduce adds up all of everybody's send buffs and gives them only to the root processor. Now MPI all reduce, and now this is one of the 2 routines. The last 2 are the important ones that we're going to be using a lot in this chapter 6. All the others, I don't use them at all in the chapter. But MPI all reduce is exactly the same as MPI reduce, except that everybody gets back buff. So everybody puts in their send buff, which still hasn't changed. It's still, processor 0 send buff is 1 through 7, and processor 1 it's 11 through 17, and so forth. So back buff of length n, which is 7, adds up everybody's send buffs, but now it passes back buff not just to a special processor root, but to everybody. So it's the same as the reduce, except that the output goes to everybody. And now we print out, after all reduce, we print out, and you see that each of the 4 processors has a back buff, which is the sum of all the send buffs. Same as, this was what processor 0 got from MPI reduce. This is what all the processors get from MPI all reduce, exactly the same. And the last routine, MPI broadcast, BCAST. This is the other important one. All reduce and bcast are very important. Others you won't see them again, but you might see them in some other context. what does broadcast do? Well, the special processor, which is still 0, so the processor 0 broadcasts its version of send buff. Now, through all of this, we never changed anybody's send buff, so they're still the same as originally. Processor 0, whose send buff is, remember, 1, 2, 3, 4, 5, 6, 7, broadcasts its send buff to everybody. So after this call, everybody has a processor 0 send buff. So now it has changed. And then we print them out, and you can see that each processor now, when we write out their send buff, it's the same as processor 0 send buff. So those have been changed now. And that's it. We got to finalize and initialize. Now these MPI barriers, if you run this, I actually did run this and commented out all the MPI barriers, everything still works because all of the routines we're using have kind of built-in barriers. In other words, like all reduce won't continue until everybody's got there. So really the only thing the MPI barrier does in this program is prevents printing stuff out in the wrong order. Like if you run this on 4 processors and comment out all the MPI barriers, you get exactly the same results, just not in this order. There, one processor will print out before the other one gets there, and so I never use MPI barrier in the linear routines, so you probably won't either, but you might use it sometime. But anyway, that's what it does. It stops everybody. It doesn't do anything except stop everybody until everybody gets there. But that really isn't necessary in these cases, except that it prevents some people from printing one thing out before the other gets there. So notice there's an MPI initialization and an MPI finalization routine. And notice this include, that will basically stick in some data statements which define all these MPI integer, MPI com world, MPI sum, all these funny variables that start with MPI. They're all defined in data statements that are stuck in there in the include statement. And so when you call MPI reduce with MPI sum will be equal to some number that we don't really need to know what it is, but it's set to something up in the include in the data statement, and MPI reduce recognizes that number as corresponding to MPI sum and so forth. So basically just make sure you have that at the beginning of each program, otherwise your variables like MPI sum, MPI integer won't be defined. So that's what this program does. It doesn't do much of anything except illustrate the use of some of these routines, but the important ones are the all reduce and the bcast. Those are the ones going to be using extensively.